Now, I'm working with the Whiskey Creek guys, but I wasn't able to get them to provide me a nice slide that showed the juvenile larva, the larval forms looking without shells. But they're having trouble, and it is looking more and more like it's related to the carbonate chemistry of the water they're growing these shells in, or these oysters in. Okay, end of part 2. And just to summarize, anthropogenic inputs driven carbon dioxide levels to at least 35% higher than they've been at any time in the last million years. The ocean is following that right along, and that elevated CO2 in water is consuming carbonate ion, making things more corrosive or less suitable for biogenic calcium carbonate minerals. And there are, in fact, experimental results that suggest harmful effects on these organisms. Okay. There's lots and lots of complications with this, and that the first one is being that it's very, very hard to mimic the projected changes. Even horrible case scenarios are hard to mimic experimentally. A typical research grant is about 3 years, right? And we're talking about something that's going to change the pH by a couple of tenths of a unit in 100 years. It's very, very hard to get NSF to pay you to do an experiment like that. Even if you can assure that it'll be alive at the end of it, it just doesn't fly. pH, as I said, is problematic. And this is something that, people kick sand in your eyes on this all the time because we say, oh, wait, we can't really measure pH well enough to do a good job at this at the levels that we're seeing here. And they say, oh, come on, I got a swimming pool or a pH kit, I can just go out there and I know immediately what the pH is. Well, ocean chemistry makes pH measuring difficult. The changes are small. In order for you to use pH, you have to be one of the best analytical chemists in the world, and there aren't very many of those people. And on top of that, as I said before, we really haven't seen any obvious suggestion that hydrogen ion itself is what's causing trouble. pH is an indicator that goes along with these other problems. It's an easy way to think about this, but pH itself is really probably not what you want to go after. And finally, the ocean's carbonate chemistry, as I said earlier, is naturally variable. There's variation in ocean pH that is greater over shorter time scales than this 0.1 to 0.3 pH unit change that we're talking about here. And I had a hard time figuring out how to analogize this, and this is, I don't know if you guys remember George Taylor, but George Taylor was big on saying that natural variability was bigger than projected trends in climate, so therefore you just didn't need to worry about it. And it's sort of like saying that, because night is colder than day, and San Francisco has the same climate as Seattle. It just doesn't make any sense. But what we're talking about here is more like there's a threshold, this mineral solubility threshold that may be something important biochemically. And the analogy that I finally came up with is, suppose there's a daycare, that's on right next to a really busy road, but it's a great daycare and everybody likes to send their kids there anyway. And somebody suggests, hey, let's just move the road over here to the playground a few feet. And they said, and it really doesn't matter if we do that because the road's already 100 feet wide and people drive all over that road. So what's 3 feet of difference in 100 feet of variability? And the issue is that there are things in the natural world that behave like thresholds or tipping points. And if you start to make your natural conditions that you experience more frequently across these thresholds, then then that's something you need to pay attention to. Okay. Finally, I guess I didn't lead off with carbon cycles in my title, but here's where we're going to end up. And this is the work that we did off the Oregon coast, and this was a project that Jack Barth, who I think has spoken here a few times before, along with Pat Wheeler and John Allen, led, and it was called the Coast Project. And this is one of these great acronyms that spells out something nice and then doesn't make any sense when you actually look at the words that go into it. So anyway, the Coast Project, we don't really hardly ever say this bottom part, we used to call it Coast. And this is work that we did on the University of Washington ship, and this is a series of transects we did across the central Oregon coast from up here at Cascade Head to down at Cape Perpetua, and we're down here. Okay. And the background here, and again, I'm probably telling you things you already know, but this system, the cascade upwelling system, is dominated by the upwelling going and forcing and its modulations. In the summertime, most of the time, we have upwelling conditions where the winds blow equatorward. Ekman transport pumps water offshore in the surface layers, and it has to be compensated for by water that pumps up from depth, from the ocean interior. Okay, so this is dense cold water, flows up onto the shelf, and if you went out there today, you'd see water that had a density of about 26.5, pushing right up almost to the beach. And it flows up through the bottom boundary layer and ultimately feeds into the illuminated layers, and it's what fuels the huge phytoplankton bloom, the big diatoms that support the fisheries here. That upwelling is a good thing. Right? We depend on it. We live on upwelling. People might remember the 2005 summer when upwelling didn't happen until about July 15th or so, and it typically starts in about the 1st of May. And in 2005, all the seabirds were starving to death, and the salmon were 50 miles offshore, and huge impacts when upwelling doesn't happen the way we think it's supposed to. And then during the winter, the winds actually blow the opposite direction. I'm sure you're all familiar with that too. That causes Ekman transport of water to go onshore here. It has to push this water back into the ocean interior. This happens to some extent in the summertime. Predominantly in the summertime, the winds blow out of the north. It causes upwelling. But once every week or so, the winds either ease off or turn around and blow a little bit out of the south, and we call these things relaxations. And during these times, you have these reversals of the upwelling circulation that's pumping water up, and you have reverse circulation that pumps it back offshore. Okay. And this water that we think is the source of the upwelled material, this dense water that's maybe 6.5 or 7 degrees Celsius and has a 34 part per thousand salinity with a density of about 26.5. We think this water takes a really long time to get here. Now, geochemists or chemical oceanographers like me, we like to think about water's age as how long it's been away from the surface, right? So how long has this water that is up here along the shelf that we're pumping up onto the shelf and fueling our upwelling system, how long has it been away from the surface? It looks like it's been away a long time, maybe 50 years, okay? And it takes sort of a funny path. And I have to say that this is pretty conjectural. I think this is true. I think there's some evidence to suggest this, but I'm not sure that it's really been proven. But we know that the water gets dense enough to sink up here in the far western North Pacific, and then it somehow gets over here. The trick is that it doesn't look like it has the same temperature and salinity characteristic here as it did at its source. And there are other tracer data that suggest that this water actually flows down to the equator, mixes with Southern Ocean and Arctic source water, goes back along the equator to the continent, where it splits, and some of it flows up to the north and some of it flows to the south. Okay? But it takes a long time for it to get from here to here. Decades. Along that path, it changes its chemistry in ways that set the tone for the upwelling. I'm going to show you some data that we collected with a vehicle here that we couldn't even think of an acronym, so we just called it Super Sucker. So far, we've been able to avoid copyright problems with the band known as Super Suckers. Essentially, we call it a vehicle. It looks like a tank made out of irrigation pipe. And we tow it through the water, and we have a winch that's computer controlled, and it makes it fly up and down through the water as the ship is moving. We have a pump down here on it that pumps seawater back up through this cable, a whole set of instruments on the vehicle that tells us about the conditions where we sample from. And then we do really, really fast measurements of chemistry on the shipboard end of things.